Good afternoon. My name is Marlene Luckner. I'm the marketing manager from Arkham Systemautomation, and I wish you again a warm welcome to our webinar. As an innovative company, Arkham is supporting its customers since 1994, primarily in the areas of product development and manufacturing. Arkham offers integrated solutions that cover all phases of the product lifecycle. As a top partner with the Smart Expert status from Siemens Digital Industries Software, we have round about 40 employees at 3 locations in Austria, and do not only offer you the extensive portfolio of software and hardware from Siemens. On top, we propose services from professionals who support you or can do the simulation and testing for you. Arkham Systemautomation and its subsidiary Arkham Engineering are the perfect combination between software, hardware, and service provider. So, let me handle the presentation to Alex Vermeulen, who will present you front-loaded test, faster and better engineering. It's your turn, Alex.
Thank you, Marlene. Yep, I will. So let me know if you can see it. Okay, and if you want, I can also put my camera on, put myself in front of the presentation. Okay. So thank you, Marlene, for the introduction. Good afternoon, everybody. Welcome to this webinar. Thank you, Arkham, for setting up this event and giving me the opportunity to present today. So my name is Alex Vermeulen. I am in Siemens DI. I am the portfolio development responsible for Simcenter testing solutions and smart vehicle technologies for the EMEA zone. The topic of today's webinar is how to front-load test for faster and better engineering. And actually, to understand the reason why we want to talk about this, let's first have a look at the industry trends and drivers. So, looking at the industry trends, we see that we are facing an explosion of complexity. We have to make products smarter by integrating mechanical and electronics and controls. And these products have to become greener, more efficient, more flexible, more reliable, and so on. And all of that we have to do in a shorter time, more cost effective. So you can question yourself, how can your engineering teams turn these challenges into opportunities? How can they make the products more powerful, but also greener, faster, but also quieter, lighter and stronger, thinner and also cooler? So how to deal with this increased complexity and have to do that all faster to market? Well, in order to allow people to do so, Siemens has developed the Simcenter portfolio. It's a portfolio that combines not only mechanical engineering, but also fluids and thermal, electronics, system simulation, and physical testing. And on top of this, we bring professional customer support and, last but not least, engineering services. Engineering services who bring deep engineering expertise, and they also do know-how transfer to our customers. So bottom line, the use of Simcenter delivers a number of benefits. It allows you to design and to engineer better products. It gives you earlier insights in the product performance. It allows you to accelerate innovation, which in the end, it helps you to gain market share and to be successful. Now, if we zoom into test solutions, which is the purpose of today's webinar, I can extract from here 4 main pillars that we focus on. The first one is productivity. You see that, as we have seen in the introduction, there's more and more testing needed because there is more and more complexity in our designs. There is also less and less time to do testing. There is less and less availability of prototypes. So what people need is to have very productive testing solutions, and that's what we focus on. Second pillar, innovation. Of course, we are doing a lot of research and development, and we bring every release a lot of new smart capabilities in our tools in order to allow you as a customer to also cope with innovation, thinking about trends, electrification, autonomy, but also how to implement new materials and so on. And the third pillar, it's really about insight. And I think that's really at the core of what we do, is to give you the most powerful solutions that help you to get as fast as possible and as deep as possible insight into your product, insight into your data that you measure, and giving you very smart, powerful analysis methods to understand the phenomena that happen in your product, but also, of course, to troubleshoot and to improve your product. And then last but not least, the fourth pillar is be certain. Be certain of what you measure is absolutely correct. Be certain of tests that you control, as you see here in the picture, for example, a satellite test, but could be another test, that is run correctly and safely. So these are the four main pillars that we focus ourselves for our testing solutions. Now, if we take a quick view on what is this Simcenter testing portfolio consisting of? Well, first, the software. It consists of TestLab, which is the widest, most complete testing platform available on the market. You can see it here in what I call the Simcenter testing wheel. It's a wheel that gives an overview of 12 applications which are covered by Simcenter testing solutions, which go from acoustics over dynamics, structures, durability, material testing, environmental testing, system in the loop testing or XIL testing, autonomous, so testing of autonomous systems, quality, which is dedicated to production testing, production line testing, thermal testing, testing of rotating machinery, and last but not least, doing transfer path analysis. So all of that is powered by tokens. So you as a customer can decide to buy tokens from Simcenter testing solutions, which gives you access to almost any of these capabilities. You see already on the screen also a video showing you the powerful user interface that TestLab Neo offers with this pivot table for automatic data viewing, with the process builder, how to automate your analysis, for example, without any programming and so on. This software runs in combination with our Simcenter SCADA's solutions that you see here in the picture, the different frames that we have. So it's really focused on high quality data recording performance, which is independent from the channel count, going from very small front ends to very high channel count front ends. So for every application, there is a suitable hardware frame. They stand for multi-physics testing, again, to allow the usage of these different TestLab applications to be used with the same hardware, so that it's very effective for you, that you don't have to use different hardware systems for different applications. This slide shows these frames a bit more in detail. So you have on the left side SCADA's XS. It's really a handheld system. You can put it in your pocket. Up to more than 20 channels. You also have digital inputs. and so on. Then you have SCADA's RS, which is the newest release, which is an ultra rugged system that you can use in any harsh condition, with a focus more on durability type of measurements. And then on the right side, you have the most versatile multi-physics testing systems. The first one, so SCADA's mobile SCADA's recorder, is battery operated, fully closed, no fans and so on, really for multi-physics testing from small to high channel count. And then the right system is called SCADA's Lab, and it's really, as the name says, intended for laboratory usage for very high, up to very high channel counts. So now going to the agenda of today's session, I mainly wanted to talk with you about four topics which are essential, which allow you to front load test and to also tighter integrate test with simulation. The first topic is model-based testing. And model-based testing, if we look at the timeline of the product development process, you see here represented by the dotted line, the moment where a physical prototype is ready, is available. Now, looking at these two curves, the red curve shows you the cost to remove detects faults in the product, and the black curve, it shows you how easy it is to make a change throughout this development process. And you see that both curves are opposite, and it's also clear that the later in the process you have to make a change to the product design, the more difficult and costly it is. So when we see the classical prototype-driven process, you see that testing is happening when the prototype becomes available, but you also see that any changes that have to be made as a consequence of this is very late in the process. Now, a model-based process aims to perform as much as possible test early in this process, so to identify problems early, reduce cost, reduce risk, and reduce the development time. So this is in the end what we want to aim for, is to move that prototype-driven process into a model-based, earlier process of model-based development. Now, model-based development also means that simulation and test have to be combined. But if we look in reality, we see that often they are separated. And here in this slide, I want to present to you a typical situation that occurs often. You have the simulation team who has the mindset that the model can solve any issue, any question, and that the model is correct, and that if there is a question, the test data must be wrong. And then on the other hand, you have the test engineer for who the test data is absolutely correct, and the model must be wrong. And the solution here is to have a mindset shift and to be able to combine test and simulation so engineers can take the best from both worlds and do that as early as possible in the process. So to reduce development time, cost, and risk, we need to combine test and simulation. So let's have a look at an example how typically the development process looks like and how it evolves. On the left side here, you see a widely applied testing process where we start with simulation, do the design, virtual testing of the system, and then it moves into physical testing of the component, and then to bench testing, and then to field testing. Now, there is a shift to a more model-based development process in order to use simulation more throughout the development cycle. And that is what I show here on the right side, where you see still the virtual testing, but then you also see the system in the loop bench testing for model validation, virtual sensing. You see troubleshooting, and of course, still the validation once the physical prototype is available. So let's now have a look at a concrete example of a wind turbine gearbox where we take two moments, moment A and B. Moment A is virtual testing in the model. So this could be system simulation, as you see here on the screen, or it could be 3D simulation. So Simcenter AIMSIM or Simcenter 3D. In moment B, the subsystem testing, these models have evolved and there is also already a physical part that we can test, that we can use to validate and to refine the models. Now, out of each of these steps, we get simulation and test data and we get simulation models. Now, the good thing is that all of them can be integrated in TestLab and we can apply in TestLab engineering analysis capabilities for example, acoustics or durability or rotating machinery. So how does that look like in TestLab? Well, here I show a first feature, which we call the AIMSIM sketch viewer, which allows in TestLab direct access to AIMSIM models. So you can just click on an AIMSIM model, you can view the AIMSIM model itself, but you can also look at the data inside the AIMSIM model. Okay, so the user can switch to TestLab, he can access this AIMSIM model together with test data, and he can start to post-process the simulation results and to validate it against test data. So if we think about model correlation, this is a very handy tool. The advantage is that you will apply the same analysis methods, the same calculations on both simulation and test data. You can really compare apples with apples. A second application is not to exchange the data from the simulation model, but is to exchange the simulation model itself. So the model can come from an AIMSIM, actually, or it could also come from another simulation software. The exchange format that we use is FMI-FMU, so functional mockup interface and functional mockup unit. So what we now do is we bring the actual model inside TestLab and we can run it in TestLab and simulate the model in TestLab. That's what you see on the right side of the screen. So these models, as said, could come from 1D or 3D gearbox models, what you see on the left side. And then we export them to FMI-FMU. We integrate them in TestLab in the process builder as an FMI block. And then we can use that for example, virtual sensing. So take data, difficult to measure data from the simulation model and combine that with physical sensors as one application. We could also input test data into the model, into the FMU, and then get the output of the FMU and then process that data to do prediction of performance of the unit in certain conditions. So this is what is represented in this slide. You see on one hand TestLab, so the input models, and then the TestLab process builder. You see here how it is, the model is embedded as an FMU. You also see there's a parallel track for processing the test data, and you see everything comes together where you can do certain analysis, like here it is done to process color maps and order sections for signature analysis. So as a conclusion, to combine test and simulation in the development cycle, we have seen two capabilities. The first one, called the AMSIM Sketch Viewer. It allows you to efficiently analyze data both from simulation and test. No need for data importing or data handling, just directly access the model. And the second capability is to integrate models in TestLab by using FMI-FMU to perform, for example, troubleshooting and engineering. You can handle big data sets. The test data in TestLab is directly fed into the model, the FMU, and TestLab will run the simulation model. So let's have a look at a practical example. Again, we stay with the wind turbine, and in this case, with the gearbox of the wind turbine. So for wind farms, the maintenance of the wind turbines is exceptionally challenging. Often, the lifetime of a wind turbine is shorter than the typical foreseen around 20 years lifetime. And the main component which lies at the reason of this is the gearbox, because the gearbox is often experiencing quite some extreme loads. So there is a strong need for the wind farm companies for a predictable maintenance of the wind turbines, and more specifically of the gearbox, to avoid fatal damages, but also complete stops of the turbines. So how is that done? This is done by calculating the remaining useful lifetime of each gearbox of each individual wind turbine. Then we apply early detection tools to basically calculate a remaining useful lifetime and to plan maintenance, to avoid damages, to keep costs low, and of course, maintain a high lifetime for each wind turbine. So in this example, how is that done? We use historic data, which is typically logged by the controller of the wind turbine, and then combine that with an accurate model representation of the gearbox, and then we calculate basically the remaining useful lifetime out of that. So this is what you can see in this slide. And so on the left side, you see a model in Simcenter 3D of the gearbox, the wind turbine gearbox. This model is then used to calculate the internal loads, and we run this model inside TestLab. We feed it with the test data, which is coming from the wind turbines, and from here we calculate the durability metrics, and we calculate the remaining useful lifetime as a parameter, as you see on the bottom side of the slide, between 0 and 1. So as a conclusion for this first part of model-based testing, we have seen different capabilities to efficiently combine test and simulation. The first one was the AMSIM Sketch Viewer to get data easily into simulation data, easily into TestLab, and to process that together with test data. The second capability we have seen is the efficient engineering capabilities, analysis features that TestLab has, like for durability, like for rotating machinery, acoustics, and so on. All of that can be applied both on simulation and test data. Then a third thing we have seen was the capability to run simulation models directly in TestLab and to really do efficiently simulation model validation, to combine test and simulation efficiently without programming, and to, for example, do things like virtual sensing or to do model correlation. Now, a fourth capability is to do all of that in a real-time context and to use real-time capable platforms to run these simulations on, and to combine that in real time with test, with physical test. And this is the fourth point I will talk about and give that through an example, actually. And this is an example for a manufacturer of a transmission, a continuous variable transmission, which is to be integrated in a motorcycle. And what we want to do here is that we want to test this transmission with the final product where it will be integrated without that final product, the motorcycle, being physically present. So we have the prototype of our transmission and we want to test it with the virtual product where we want to integrate it. So the transmission is the whole prototype, including the controls, and we will run the rest of the motorcycle as a virtual model, real-time capable on a real-time system. So we will, on that bench, we will have two motors, one both driving the transmission, one representing the input force from the engine and the second one representing the load from the motorcycle. We'll add physical sensors on the transmission, like accelerometer, strain gauge, and so on, that we will connect to the SCADA's measurement system and test lab. And we will feed that also back to the real-time system, so the real-time system and the real-time model knows where the transmission is. And we connect all of that to test lab. So how does it look like? That is the setup where you have the transmission on a bench with the drives and then the power electronics. This is how it looks like in reality. And where on the bottom side you have the SCADA's lab system, and under the SCADA's lab system you have the Siemens real-time system where the real-time model runs on. So that's one example how very efficiently you can upfront in the engineering process test the component that you developed in the full realistic integration with the final product without the final product even being present, which allows you to much faster check integration issues, check performance, and of course, optimize your product performance if needed. Another thing I wanted to share with you is that we can also help you to convert existing test benches, which maybe run just a number of loading cycles or static regimes. We can help you to convert those, and that's what is represented on the left side in the screen. We can convert those classic test benches to XIO testing, to a smart test bench, where, as you see on the right side, then we add a number of components. We add a real-time system where test lab real-time runs on, where then you can run real-time models that can come from Simcenter AMSIM, Simcenter 3D, Simcenter Prescan, or from any other code through FMU. We connect that with Simcenter SCADA's measurement systems who measure all kinds of physical sensors on the bench, connect that to test lab, and also, of course, the real-time system as a user interface where you can control and you can monitor the test. And as such, you can test your product in real-life conditions without real-life conditions to be physically present, which gives, of course, that's the purpose of today's meeting, a lot of advantages to upfront these testing capabilities in your engineering cycle. So that was the first part of the agenda, which actually brings me to the second part, because we have been talking about real-time testing with real-time capable models. Well, the second agenda point is about XDT, so executable digital twin. Now, to quickly recap, what do we mean with a digital twin? Digital twin, that's a precise virtual representation of a physical asset, physical product or process. It is used across the life cycle of that product, and we use it to simulate, to predict, and to optimize the product as such. It can be made up of different representations, models. Could be in 1D, 3D simulation, and so on. Could be data based only. So it can have different representations based on the aspects it has to represent. It's evolving throughout the life cycle of that product, and very important, to make it closed loop, we need to make a bidirectional connection between the physical asset and the digital twin, so the virtual representation. Now, to run these digital twins, we need to make them executable. We need to make them real-time capable to run them. For example, in the design phase on a real-time capable system, as I have just shown, in combination with measurement system like TestLab. In the production phase, they can run on an industrial computer or an edge device. And in service, of course, we can collect a lot of information from a lot of machines or products in use and run the XDT on cloud. Some use cases to bring the real world into the product design optimization. So the first one, and I will go a bit more in detail in the next slides, is by doing smart virtual sensing and to basically measure the unmeasurable. Bottom line, what is it? You can measure a number of simple measurement points, easy to access, and you can expand that by using an accurate model and get from that model with these limited measurements a whole set of reliable virtual sensor data points. A second example is really on model-based system testing, system-in-the-loop testing. Suppose the example here where you have 3 different or multiple designs for a robot clamp. Well, you can test the best one. You can verify the performance without having the physical integration with the robot. You can have a model of the robot running as a model on a real-time system and test these physical and virtual representation of your integrated product at the same time, as if it physically exists. And a third example was what I said already. So you can take data from products in use, collect them on the cloud, have an XDT run on that data, identify critical cases, and then use a digital twin to optimize the behavior of your product, the performance for these critical cases. Now there's a creation and a deployment process. In a nutshell, you have your physical assets, your products. You create simulation models from this in 1D simulation, 3D simulation, and so on. Then you use reduced order modeling techniques to make those models real-time capable also without losing information, to also define these virtual sensors, so to connect with the test data, and then you can deploy them as an XDT on real-time capable systems or on the cloud. So a first example I want to talk about here, it's what I said already, smart virtual sensing. And so where you have always the balance between the physical world where we cannot measure everything. We always have to choose places, some critical points where we want to put a sensor, and then we take that data. And then you have, of course, the virtual world. You can simulate anything with a model, but we are not always sure that our simulation model is fully representing the reality, because some things are very complex and are complex to represent by simulation. So smart virtual sensing, what do we do? So we use physical sensors as an input to the XDT, to the digital twin, which then gives us online, so in real time, virtual measurements at any location that we can get from the digital twin by combining it with the physical sensors. And then also the tool, which is nice, helps us to automatically define the optimal locations for these physical sensors that are required to make the executable digital twin work to do smart virtual sensing. How does that process look like? So you start, in this case, with the model in Simcenter 3D. You do the classical correlation and model update to make sure that your model is correct. Then you use the smart virtual sensing tool, who will allow you to take the input data to define where your measurement points are and to connect it with the data to define your smart virtual sensing positions. And then in the end, to export that to an XDT. And as an FMU, you can then choose to integrate it in TestLab to, for example, run it as an XDT in TestLab, but you could also import measurements in Simcenter 3D. And of course, you can also do model-based system testing, as we have just seen. In operation, you could use a real-time system with the help of our live twin app, run the XDT, and for example, to cover instrumentation gaps. And with limited instrumentation, get a lot of info from your machine. But as said, you could also link it to the cloud and do, for example, model-enabled maintenance tasks. I will skip this video because of time. Let's have a look at two practical cases. The first implementation customer case I want to show you, it's a fatigue test on a wind turbine blade. And each of those wind turbine blades, for new designs, they have to go through a test to ensure that fatigue life corresponds to the requirements. Now, such a test, as these blades are huge, require instrumentation of hundreds of strain gauges, which is a big effort to instrument them, of course. And the other issue is that, challenge I would say, is that as these tests run at low frequency, you need a long time, months of time, to run these tests. So this is quite challenging and not so optimal to redo that every time for every change of blade design. Now, an optimized process by using an XDT consists of instrumenting not at hundreds of points the blade, but just at tens of points. And by combining these limited measurement points with an accurate XDT model of the blade, we can define all these virtual sensing points where we will take virtual measurements from. And as such, we can run the test campaign with a very shorter and limited instrumentation time and test setup. We can get out of the combination of this limited physical sensor measured and the XDT, we can get as an output much more information. We get the results from 10,000s of points, just as we have it from an FE model. And even more, we can also use this XDT now to predict where the test is and where it will go to. And so to predict basically durability, predict fatigue and failure. So with this solution, for this application, 80% of the time for instrumentation was reduced and 30% of cost for hardware, sensors and channels was reduced. See here also, sorry, second video don't seems to run. But you can see it in the left video, sorry for that. how it looks like when we also apply augmented reality to this. You see the person bending the blade and fatiguing it. And you see on the left side on the screen the result of the XDT based upon a limited measurement sensor set, generates stress and strain fields, very fine, very detailed, of every point, the complete blade, just like that in real time. Second example I want to share with you, it's another customer case, which is different here. In this case, this is a truck manufacturer with, who was having some issues with the shaft, the rear shaft of the truck during manufacturing, during assembly breaking, which caused safety issues for the operator who could be injured, but also obviously impacted the delivery of the product to the customer side and potential failure also, obviously. So the customer wanted a fast solution to this problem. The problem was actually that the anchorage of the axle was failing during the production, assembly, actually. Now, if we use the existing process of the customer, the issue was that there was no possibility to put sensors at the hotspot locations. So the only possibility was to use sensors from faraway locations. And that's what you see here on the picture. And from there to use a model and to try to estimate those critical locations. Now, this would require to make a dedicated test setup and use also load cells to apply to the test setup by using load cells a dedicated load, and then to measure all the output, then to do forward FE simulation, run a number of simulation loops, 5 in this case, to improve the accuracy of the result, and then finally the result would be obtained. This process would take 18 weeks of time, plus the challenge that by making that test setup with the load cells and the external load, it's very challenging to ensure the correct boundary conditions for this setup. Apologies for the noise here, but I have some alarm which is outside ringing. I cannot stop that. This was not an acceptable process for the customer. So what is the solution that Siemens applied? Well, we used Simcenter 3D model. There we used a smart virtual sensing tool to, as I explained, determine the measurement points, the virtual sensing points, and so on. Export that to an XDT model, import it in TestLab as an FMU. In TestLab, we connected the measurement locations at the faraway locations and used that as an input into the XDT model, which then generated the strains at the hotspot locations where no measurement points or sensors could have been put. The results, how does that look like? Well, around 20% confidence bound at the hotspot locations, which was very acceptable to the customer, and also having to take into account the simplifications that were applied to the model in order to work fast. So you have to keep that in mind. To conclude on this, basically the whole process that we applied with XDT allowed to accurately determine the strains and stresses at the hotspot locations, and by doing that in a reduction of time and cost with 60%. So just to show you 2 practical examples of how to apply XDT and the benefits that it can bring. So this brings me to the third agenda point, model testing. And why I want to talk about model testing shorter now than the first two topics is because it's still important if you want to apply simulation throughout the engineering cycle, more than is done today. You want to tightly connect that and integrate it with tests. You need to make sure that you have accurate simulation models. Now, if you want to be sure about that, you need to make sure that you perform proper model testing and model analysis. So let me revisit the procedure. Model testing, model analysis. For model testing, if we stick with experimental model testing, we apply a force, artificial force to our structure. We measure the responses with accelerometers, as you see here, and we calculate the frequency response functions, FRFs, as is represented in the left graph. Then we apply model analysis. We take all these FRFs and we apply a curve fitting technique in order to determine, to calculate what you see here on the right side, stabilization diagram. And the goal is then to select the correct poles to then finally calculate all the model parameters, being the natural frequency, the damping ratio, and the mode shape. Now, the challenge, one of the challenges lies, of course, in the fact that your data is not perfect. Every data contains noise. Your structure is not perfectly linear, has complexities, has global and local modes and behavior. So there are some challenges with your structure and your data. And so to ensure that what you get out of this is fully user independent, so that you determine your model results fully as related to the structural behavior of your component and not to who does this work, you need strong tools that can handle this. And that's what I want to show here with this stabilization diagram. So for people not familiar with this, here on the x-axis, you have the frequency range in hertz. And then here you have the model order. And here you have the amplitude of the FRF, the overall FRF. And what the job is to select the right poles and then to calculate the mode shapes and so on. Now, here you see a lot of noise, I would say, so calculational poles, which makes it very difficult to select the right poles. Now, what we bring as Siemens is we have curve fitter who is called Polymax, who works not in the time domain as the previous LSCE, but he works in the Z domain, providing crystal clear stabilization diagrams that help you very reliably, correctly select the right poles and calculate the right model parameters in very user-independent way of working. We even have implemented the skills, the expertise of a model analyst in a tool in TestLab, so that you can select these poles with one button click and have an even easier job to do this. We have also done a number more. I see one picture is not coming. Sorry for that. We have even stronger capabilities developed with Polymax Plus, which is used for even cases with even more noisy data, that it can even get better results out of that. And the most recent development was MLMM solver, difficult name, which does further help to optimize the model, to reduce the scatter, which is typical for this iterative process on very difficult cases. Of course, this, I see I have an issue with my animation. So again, apologies for that. But just to say that our testing solution for model testing doesn't stand alone on its own. It's fully integrated with Simcenter 3D. So on the left side, you see pretest analysis, where You can in Simcenter 3D determine the locations where you have to put sensors, the locations where to excite the structure for the model order of interest. Then you take that into test lab, it's tightly integrated, seamlessly works. You perform your model test, then you use the results of your model test to correlate and update your simulation model in Simcenter 3D. So if you use other tools in Simcenter 3D, like ANSYS or others, you can perfectly also do this because we also connect to other simulation codes. This brings me to the last point on the agenda, digital image correlation. I see I'm losing more pictures, so I hope this will not continue like this, or maybe Marlena, I think I will have to stop sharing for a moment.